Using portable and child-friendly functional near-infrared spectroscopy, or FNIRS, we recorded brain responses to a print-speech task from children in rural Cote d'Ivoire, where literacy rates are low and children have widely varying literacy skills. We attempted to train a deep learning model to classify children's portable neuroimaging data into varying degrees of literacy in an attempt to identify if there is information relevant to literacy development in that signal. Our CNN LSTM model learns both spatial and temporal features available to us through the use of FNIRS. On an initial training set, our model was sensitive towards detecting non-literate children from semi-literate and literate children, but overall performance was negatively affected by the small data set. Overall, we found some evidence that the patterns of brain activity in these children varied with level of literacy, and it will help us in the future to improve the model's accuracy and identify the spatial and temporal aspects of brain responses associated with literacy development. To hear more about the specifics of this study, please stay tuned. A lot of what we know about the cognitive neuroscience of literacy comes from populations in high-income countries with widely accessible schooling and high adult literacy rates. However, literacy development might differ with important environmental factors, such as how early children begin learning to read or the availability of literate adults to support their education. So, in lower and middle-income countries where education and literacy rates vary, children's outcomes might be a lot different. These differences also correspond with places where neuroimaging tools are not often available. As a result, the cognitive neuroscience of literacy in low and middle-income countries is an important experience in child development that is systematically understudied. Previous literature suggests that FNIRS data contains features that lead to accurate classifications of subtle behavioral measures, like emotional valence of a music video. We attempted to extend a previously successful deep learning model proposed last year by Bendara, Bellapassalar, and Hirschfield to classify children's FNIRS data by literacy status in an attempt to identify what features of the FNIRS signal might be relevant to categorizing a child's literacy development. We used portable and child-friendly FNIRS imaging to record changes in cortical oxygenated and deoxygenated hemoglobin from children in Cote d'Ivoire during a passive print speech task. The recordings consisted of a series of 5x9 images that represent changes in brain activity over time while children were reading or hearing both words and non-words. Separately from the imaging experiment, each child also performed a French adaptation of the early grade reading assessment, which we used as our measure of literacy. Each child was also asked to read a set of 50 words in 1 minute, with the number of correct words being their score. We defined literate children as those reading 40 words or more, semi-literate as 10 to 40 words, and non-literate as under 10 words. The literate group represented 11% of our dataset, semi-literate was 39%, and non-literate was 49%. Our CNN LSTM model learns both spatial and temporal features present in the sequence of brain activation images. Useful features help the model increase classification accuracy during training, and irrelevant features are eventually ignored. A basic example: to classify a tree, you might pay attention to the shape and size of the leaf, but you would probably ignore the color of the leaf, since most leaves change color and do not differ between trees. In this example, the leaf provides a feature that allows you to draw a distinction between trees, whereas color as a feature would not. The CNN model, which is most commonly used for basic image recognition, allows us to extract the key spatial features of each image and pass these features to the LSTM. The LSTM is then able to look at the small time window of these images and generate temporal features and pass these to a fully connected layer. The fully connected layer will always output a series of discrete features that, while it's usually opaque to us, represent the aspects of the data that predicted the trained classifications best. Each discrete feature is the result of a weighted sum of all features described by the LSTM. The set of weights used by each of the fully connected features varies, allowing for each discrete feature to represent individual aspects of the data. While the first fully connected layer's output is difficult to interpret, the second fully connected layer has only 3 outputs, each of which represent its probability of being classified into one of the 3 literacy categories. We trained our model using a 5-fold cross-validation method, with 120 runs of the task resulting in 24 runs being held out for testing, after using 96 runs as training. Thus, when all 5 folds have been completed, all 120 runs have been tested by the model. While overall classification accuracy did not significantly exceed chance, cumulative D-prime scores were 0.603, 0.511, and 0.295 for literate, non-literate, and semi-literate respectively. The result shows that the model is more successful detecting non-literate children, but struggles when presented with semi-literate and literate children, suggesting variation in the patterns of neural activity present in children with varying degrees of literacy. The representation of the fully connected layer shows that each of the 3 categories have clusters of correctly classified children at each point, suggesting that literacy is a learnable feature present in our data. This finding will allow us to, in the future, identify patterns of activation associated with varying degrees of literacy that are not evident in traditional analysis models.